All right, thank you all for coming here and listening to these exciting set of talks. I've been like super enthused since morning, and thank you, Dimitri, for setting the stage for organ transplantation. And this talk is about some new types of organs that are being discovered at this very moment in the last couple of years. And so I'm going to talk about the impact of cryopreservation and xenografted organs on the already complex organ transplantation pipeline. And I want to say a huge thank to the SERC seed grants for helping us jumpstart this collaboration. Our team here has some fantastic students, Thomas and Madeline. Madeline is actually in the crowd there. And we have master's students, Jesse and Prateek. And our collaborators, Dr. Korkut Aygun, Heidi A., Mehmet Toner, and David Krohn have actually been involved in successfully transplanting a first pig-edited gene organ into a human, and they're actually looking at clinical trials starting in 2025 for this technology. They've also successfully shown cryopreservation for pig and human kidney partial freezing. So in that context, let me give you some numbers again. So each day, 18 Americans die waiting for an organ transplant. Thousands never make it to a transplant list. Out of these, end-stage organ failure alone accounts for around 730,000 deaths in the US, and it's estimated that 30% of these can be saved with an organ replacement. So with these staggering numbers, when we preview these exciting technologies that are about to, that are already starting and rapidly rising in growth of cryopreservation and xenografting, we have an opportunity. So with these breakthroughs, the opportunity is that we have a chance to reshape the organ transplantation, the future of organ transplantation. But the question isn't just can we do that, it's where and how should we target these new technologies to have a positive impact on the existing organ transplantation pipeline. How should we assess that? Because look, these technologies are currently being passed through clinical trials, so there's not enough data. So we have to rely on the data that already exists in the current system with the current practices and find opportunities where these should enter the market in some sense, right? So as Dimitri already mentioned, organ transplantation is actually a very complex process. It's beyond the organ transplantation policies. There are various factors on what is the kidney quality. So these are donor factors. What are the recipient factors? Things like HLA compatibility, things like sensitization, things like, what is the age of the recipient and how sick and how urgently they need that organ. There are human factors on, what is the surgeon's estimate of the benefit and the risk of doing an organ transplantation with a particular kidney that becomes available. There are logistics and timing, which include geographic distance, the time to offer acceptance, which might already deem that organ unviable, but perhaps we could save that using cryopreservation. Cryopreservation is this, you freeze an organ to very low temperatures so that you can extend its viability, not just for 24 hours, but for days. And that creates massive opportunity because you could preserve even mediocre quality organs and make them available across the US and across the world even. And there are institutional and policy factors that not just come from national policies, but there might be local and regional policies that impact organ offer acceptance, right? And so what we want to do is we want to look at all of this data that already exists, and we want to use AI to help us understand where are the gaps in supply and demand, where are the opportunities for xeno and cryo organs. But this is a hugely complex medical decision-making space. And what we would like is for that AI to know also where it is uncertain. We don't want a system that can only predict and prescribe, but we want a system that is very transparent about its errors, right? So our goal is not to automate the process, it is the augmentation of decision making using prescriptive AI, which is transparent about the errors that it makes. And that is a big open question. There's a lot of research that's currently happening in trying to calibrate AI models and think about what are the errors in different instance spaces that they make. And so we are going to try and bring that thought process into the space of organ transplantation. So our first question is, when is xenografting most useful? So which types of organs are more in demand, but there's not enough supply? And if we could actually create these tailored gene edited pig organs, if we could target specific profiles, then could we actually close that supply demand gap? Could we actually provide better kidneys to patients who really need them? And so here is a perspective from a patient's, from a patient's perspective, what happens when they're made kidney offers, or what might they expect in an organ transplantation pipeline. So here is a patient, or you can think of it as a pool of patients that are looking for an organ that is a good fit to them. In the pipeline, there will be many organs that will be offered to patients with similar profiles. These organs can have a higher quality and they can have lower quality, and so this is measured by something that is called the KDPI, which is a measure of organ quality for kidneys, how useful, how beneficial these kidneys are going to be. And once a patient is offered all of this portfolio of organs over a period of time, and I'm thinking about a patient cohort, but simplifying on this slide, if I typically match patients of this sort with an organ of a high quality relative to the offers that they've gotten, I say, well, there's enough supply of such organs, accounting for time effects, for waitlist effects, for placement effects, and so on. There's enough supply of good organs, and they can be matched to an organ with relatively high KDPI. But on the other hand, we see cases where there are patient groups that are, despite an organ, the distribution of organs or the types of organs that are offered to them, have higher KDPIs. They often end up getting lower quality kidneys. So they end up getting not the high quality kidneys that would have appeared in an offer to them in the system, but they end up getting low quality kidneys. And so for various reasons, we call that a supply demand gap. So we say that if something like this happens, that's an opportunity for xenografted organs, because I've identified a patient population that for various reasons in this complex pipeline are actually not making use of the high quality organs that are getting offered to them. And so our question here is that let's look at all of the PTR data. So we have, this is the match run algorithm, which makes offers to patients through policies that Dimitri discussed in his talk. And so we have around 25 million records here. And we want to use AI to automatically find sets of patients with various recipient characteristics where then they don't have access to high quality kidneys in that system. Right? Okay. So we can create metrics. These are statistical metrics. They are just a single number that we evaluate for every patient, and we evaluate it for a cohort of patients. And we can create these models that tell us where the nodes are redder in color, that's where there's excess supply. Where the nodes are lighter in color, that's where we are kind of closing that supply demand gap. If the nodes are white, that's where the demand is much higher than the supply, right? And so let's unpack that a little bit. So this is in one of the regions. So in this talk, I'm going to consider 3 regions. There are 3 big cities with a lot of transplantation centers. They're demographically very diverse, and so, but we are going to obfuscate the names, but just call these regions 1, 2, and 3. In region 1, we see this node with a very red color, which means that if I look into that node, the patients have been offered kidneys of quality that look like that. So that's worse kidney quality. These are the offers, the blue histogram. And the acceptances are skewed towards the right, which means that this is higher, relatively higher quality kidneys were accepted more frequently than the low quality kidneys. And so that tells me there is no supply demand gap. In fact, supply is enough, and there is there is not demand that we cannot meet with the current availability of organs in the system. Let me show you another example. This is supply demand gap in region 2, and here we see a node which has a negative value. And what that negative value means mathematically is that there is more demand than potential supply, when I unpack the offers that patients with these characteristics have gotten. So these patients are the ones that are not blood type O and where a particular allele B162 is present. For these patients, the mean quality of kidney that was offered to them is better than what was actually accepted. And so the offers tend to be towards lower kidney quality rather than higher kidney quality, as in the previous example. So this automatically helps us, this system automatically helps us go through millions of patient organ offers and automatically detect areas where xenografting can be very useful. Next up, I want to think about cryopreservation. And cryopreservation, as I said, is this scientific technology of kind of decreasing the temperatures and freezing the organs to such a low amount that you can preserve the organ for a much longer time beyond 24 hours of kidney viability, but also you can do it in a way, you can slowly increase the temperature in a way that the organ still remains viable. And our question is that, there is a lot of kidneys, a lot of organs that are actually unused in the system, they are non-utilized, and can we actually utilize them potentially by cryopreservation? So some statistics again. So here we are looking at diseased donor organs in this space, and the kidney non-use in 2023, and this is a slide from SRTR, shows that there were 5,000 donors with from whom at least one of the kidney was not used. There are approximately, there were 8,500 kidneys that were non-used from these 5,000 donors, and there were 26 million offers that were made for these kidneys that were ultimately not used. So imagine an organ becomes available, it is getting matched and offered to patients by their priority on the wait list. By the time somebody could even accept that offer, that kidney is already not viable anymore, right? And so there is a lot of, it's over 28% of the kidneys recovered from deceased donors were actually not used in 2023, and that's a huge opportunity to use cryopreservation. It's also a huge opportunity to automatically understand if a kidney is not likely to be used by the first 500 patients, why not bypass and create an expedited offer that can place that kidney faster, and potentially somebody can benefit from it. So with that in mind, we thought about, what are the organs that are viable for cryopreservation? There are definitely factors that correspond to high creatinine levels, low filtration rates, old kidneys from very old donors that make them not very viable for use. But what about kidneys that are kind of in that mediocre range that could still be useful if they were just transplanted early enough or cryopreserved and transplanted later in the system? So that's our next question that we considered on how can we use AI to predict how different regions in the US, so we've just done it for 3 regions so far, how different regions in the US will respond to an offered non-utilized organ in the system by learning from past decisions. So we are taking the current system, the current organ transplantation pipeline, which does not have an estimate of the risk, it does not have cryopreserved organs in the pipeline, but we are trying to learn from that data. And again, we are going to keep our eye towards uncertainties in that pipeline and errors in these predictions. So we took all of this data, we went very happily, we developed our machine learning models, we did some feature selection, we got input from doctors. Because of the policy changes, we incorporated years, we had low and high KDPI kind of variables, we had regional models that predicted what is the maximum predicted acceptance of organs across the 3 regions, and these models are different, reflecting regional practices. And then using all of this, we wanted to predict accept or reject. But of course, this is a system that's using all of this data that exists, and the system can make mistakes. So let's look at the accuracy of this. The accuracy that we got was fantastic. We were very happy when we saw that, right? But an accuracy of 98%, 99% from accepted from the PTR match run data has to be taken with a pinch of salt. Why? Because most of these organs are actually rejected. Most of these offers in the system are rejects, right? So even if I predicted a reject for every organ, I would get an accuracy of 98%. So accuracy has to be taken with a pinch of salt, and instead we can look at precision accept. What is precision accept saying? For offers that were actually labeled as accept, how many were actually accepted in the data? So for organs where I actually predicted an accept, how many of these were actually accepted by the doctors? That's when a system can be really useful, right? And so across these three areas, we actually saw that region 1 had a 0.65 precision accept, region 2 had 94, which is fantastic, and region 3 had 85%. All right. So we thought to ourselves, is our AI making mistakes, or is the data bad, or is the decisions of the doctors very noisy? Like, what is going on here? Why don't we have the same precision accept across? And a little bit of insight into that is that indeed region 1 has much sparser data than region 2. So there is that effect of not having enough data across. And we trained national models and they didn't help us. So we said, can we understand what are these regions based on organ quality where I will have more fidelity in my prediction versus where I know that my prediction is uncertain and I should not make a decision. And so in that vein, so with that thought process, we looked at what is the performance of these models across the 3 different regions. And as you can see, the performance is not uniform. So as the kidney quality changes, for very low kidney quality, so that's the end of the bar chart here, a lot of kidneys are rejected, and so the decisions are much easier. For very high quality kidneys, a lot of kidneys are accepted and decisions are easier, but you will see a dip when the decisions kind of become in that gray zone, right? And so our thought process here, and let me skip through these slides, was that we want to be able to navigate these predictions with the amount of uncertainty in my AI model. And here is the kind of trade-off that we would like to make visible to our team and to the transplantation system. So in region 1, the expected number of placements for the set of kidneys between 0.5 and 0.6 kDPI, so this is mediocre range, was around 23 to 57%. That's kind of our range of how uncertain we think the model is. And the precision accept of that model is 0.43. So every time I'm giving you, in some sense, a range of what I think the benefit can be from placing this organ into region 1, region 2, or region 3, and I'm also combining that with the precision accept across for these kinds of organs. So this is a simplified slide to tell you that there is a trade-off, right? I can go with a very certain model in region 3 that almost saves no kidneys, or I can go with a model in region 1 that is much less certainty and saves organs in that range. And so one might think that if I want to have a trade-off, I might go with region 2, which has a 0.65 precision accept. So with all of this, we are very excited to understand the trade-offs, develop more machine learning models, kind of open up that black box for physicians and decision makers in the system. And we are developing currently web tools to bridge this to practice. So for any organ that becomes available in the system, we have a web tool that's not online yet, but will be very soon, where you can ask for the predictive models for different transplantation centers in the regions that we've considered. For the organ, we can show you that this organ looks like very similar to all of these organs that were actually rejected. You can explore what organs in the systems, which past offers were rejected, which was similar to these, or if there is a possibility of placing that organ in that center. So that will help us create these expedited offers that can help with the use of cryopreservation, decrease non-utilization of kidneys. So with that, thank you all for listening, and I'm very happy to take questions.
Questions? Yes, go Are you using the region's data to train the region's model?
We are, yes.
Or you're not using it across the 3 regions?
We tried training a model across the 3 regions and fine-tuning for the region's data, and that ended up not having a higher predictive power, as we can see on the test data for the regional models themselves. Sometimes we also find that the variables that are being selected, so we have a staggering number of 800 variables that go into prediction for every offer. And the variables that are selected that are most predictive are often different for the different regions. So some of the key variables are the same, but you see insurance pop up in one of the regions. And so that's, that's a potential, there's some correlation there that we would like to explore.
Great. Further questions?
Thank you so much for this presentation. I have some questions about the AI techniques you use. So you use XGBoost. Did you also consider using like transformers or CNN or any other models? If so, what were the difficulties when trying them?
Right. So we used LLMs. So we actually we followed up on a very nice recent work from Dimitri's group actually on tap text, creates which takes a tabular data, creates that into text data, creates an embedding from that, and augments the XGBoost model. And we found that for some regions it had a slight benefit, but for others we've not seen the benefit yet. So there is more exploration to be done there. Yeah. But perhaps some of these transformer augmented models could help create more context. But I think what we are seeing is that there's enough noise in the system that you're kind of reaching the limits of what can be predicted here.
Awesome. Any further questions for Swati? Yes.
Hi, is it possible that the machine learning actually is learning the wrong things and emphasizing the wrong things continually?
So we are trying to make sure that that doesn't happen. So using all of our various analysis, so we've done like SHAP analysis, we've tried to understand what are the different factors that go into that decision making, we've talked to the doctors, we've kind of, it's that we've kind of tried to check at every step with the domain experts in this area to see if things are aligned with what they would expect. So and sometimes we've been able to see examples. So for example, we have a model that predicts non-utilization in the current system. Is this organ going to be non-utilized or not? And we do see, when we predict non-utilization, we see areas of high creatinine and high age donors that pop up as very certain non-utilized in the system, right? So every time we train a model, we try to back up and then stress test that on, okay, what are the distributions, where are the errors, what is it saying? Is it saying something that we believe is true or not? And this space is very complex. So I feel like we are peeling an onion. Every time we peel a layer, there's another layer to peel.
Great. And final question.
How are you planning to prevent model drift in the future?
So one way that we are kind of thinking about this is incorporating year and kind of time trends in the model, specifically with respect to policy changes. As policy changes, there is a lot of change in the system. And so you have to, in some sense, stay current, but also incorporate like some of the resistance. Like in one of the analysis we did, we thought, we found some evidence that, centers that are more reputed and that they just have a higher friction in kind of changing their policy across the years. So they change the policies much slower, and centers that are much smaller, they are more actively changing the policy. So there's a lot to be done in that space, and I think we are only scratching the surface.
Well, thank you so much.